Why is the channel capacity C related to the mutual information between X and Y? Consider the block diagram for the communication system and observe that the random variables W, X, Y, and W hat form a Markov chain. Now consider the information diagram for this Markov chain. Since we assume that the encoder is deterministic, the entropy of the X sequence given W is equal to 0. This is shown in the information diagram. Likewise, we assume that the decoder is deterministic, so that the entropy of W hat given the sequence Y is equal to 0. This is shown in the information diagram. Now for reliable communication, W, the message, and W hat, which is the estimate of the message, should be essentially the same, so they are essentially functions of each other. That is, entropy of W hat given W is equal to 0. This is shown in the information diagram. And entropy of W given W hat is equal to 0. This is shown in the information diagram. Now we see that the setup of the problem actually imposes a lot of zeros in the information diagram. From the information diagram, we see that the entropy of W is equal to the measure on the atom marked by the red dot. Likewise, the mutual information between the input sequence and the output sequence of the channel is also equal to the measure of the atom marked by the red dot. Therefore, we see that HW is equal to IXY. That is, the entropy of the message is equal to the mutual information between the input sequence and the output sequence of the channel. This suggests that the channel capacity is obtained by maximizing the mutual information between the input sequence and the output sequence, and we are going to see that this is equivalent to maximizing IXY, the mutual information between the input and the output of a single use of the channel. We now look at the building blocks of the converse proof. First, observe that for all I from 1 up to n, the mutual information between xi and yi, by definition, is less than or equal to c, because c is the maximum of ixy over all input distribution pxy. Then, summation I equals 1 up to n, ixi is less than or equal to n times c. To be established in lemma 7.16, the mutual information between the input sequence x and the output sequence y is upper bounded by summation I equals 1 up to n, ixi yi. Therefore, 1 over n times log m, which is the rate of the code, is equal to 1 over n times log of the size of the message set. Because the message is chosen uniformly, this is equal to 1 over n times the entropy of W. As we have seen, for reliable communication, this is approximately equal to 1 over n times the mutual information between the input sequence x and the output sequence y, which from the above is upper bounded by 1 over n times summation I equals 1 up to n, ixi yi, and that is upper bounded by c. So, essentially, we have the ingredients for proving that for reliable communication, the rate of the code cannot exceed c, the channel capacity. We now prove lemma 7.16, which asserts that the mutual information between the x sequence and the y sequence is upper bounded by summation I equals 1 up to n, the mutual information between xi and yi. First, from the previous proposition, we have the entropy of the y sequence given the x sequence is equal to summation I equals 1 up to n, the entropy of yi given xi. Then, the mutual information between the x sequence and the y sequence, which is equal to the entropy of the y sequence minus the entropy of the y sequence given the x sequence, by the independence bound, is less than or equal to summation I equals 1 up to n, the entropy of yi, minus summation I equals 1 up to n, the entropy of yi given xi. And this is equal to summation I equals 1 up to n, the mutual information between xi and yi. We now give the formal proof for the converse of the channel coding theorem. The key idea is to apply Farnell's inequality to rigorize the approximation that we have used in the argument. Let R be an achievable rate, that is, for any epsilon greater than 0 that exists for sufficiently large n, and nm code such that 1 over n log m, which is the rate of the code, is greater than R minus epsilon, and lambda max is less than epsilon. Now consider log m equals entropy of W, because the message is chosen uniformly from the message set. Now the entropy of W is equal to entropy of W given W hat plus the mutual information between W and W hat. By the data processing theorem, the mutual information between W and W hat is upper bounded by the mutual information between the x sequence and the y sequence. By lemma 7.16, the mutual information between the x sequence and the y sequence is upper bounded by summation I equals 1 up to n, the mutual information between xi and yi, which is at most equal to n times c. By Farnell's inequality, the conditional entropy of W given W hat, that is, the first term above, is less than 1 plus PE, the average probability of error, that is, the probability that W is not equal to W hat, times the log of the size of the message set. And this is equal to 1 plus PE times log m. Then, from step 2, we have log m is less than or equal to entropy of W given W hat plus NC, where by Farnell's inequality, the entropy of W given W hat is less than 1 plus PE times log m. Now PE, the average probability of error, as we have seen, is less than or equal to lambda max. And by our assumption of the code, lambda max is less than epsilon. Now moving the term epsilon log m to the left-hand side, we have 1 minus epsilon times log m is less than 1 plus nc. And moving 1 minus epsilon to the right-hand side, we have log m less than 1 plus nc divided by 1 minus epsilon. Upon dividing by n on both sides, we have 1 over n times log m less than 1 over n plus c divided by 1 minus epsilon. Therefore, following our assumption on the code, we have r minus epsilon less than 1 over n times log m, and 1 over n times log m is less than 1 over n plus c divided by 1 minus epsilon. So we obtain r minus epsilon is less than 1 over n plus c divided by 1 over epsilon. To complete the proof, we let n goes to infinity so that 1 over n goes to 0, and then let epsilon goes to 0 to conclude that r is less than or equal to c. We now discuss a corollary that gives a lower bound on PE, the average probability of error, when n is large. Consider the highlighted inequality we obtained in step 4 in the proof of the converse coding theorem. From this inequality, we obtain PE greater than or equal to 1 minus 1 plus NC divided by log m. Multiplying by 1 over n upstairs and downstairs in the fraction, we obtain 1 minus 1 over n plus c divided by 1 over n times log m. When n is large, the 1 over n upstairs is approximately equal to 0, so this can be approximated by 1 minus c divided by 1 over n times log m when n is large. This lower bound on PE is illustrated by the figure on the left-hand side. We now give an asymptotic analysis of PE when n is large. As we have shown, for large n, PE is lower bounded by 1 minus c divided by 1 over n times log m, where 1 over n times log m is the rate of the channel code. The above lower bound on PE says that if 1 over n times log m is greater than c, so that c over 1 over n times log m is less than 1, then PE is bounded away from 0 for large n. This is illustrated in the figure on the left-hand side. If we take the rate of the code to be strictly greater than c, then PE, the average probability of error of the code, when the block length n is large, can only take a value in the range colored in blue, which is bounded away from 0. This asymptotic lower bound on PE also implies that if the rate of the code is greater than c, then PE is strictly positive for all n. For the details, please see the textbook. Also note that this asymptotic lower bound on PE tends to 1 as 1 over n log m, that is the rate of the code, tends to infinity.